Okay, we're going to start Chapter 10 right now. Chapter 10 is all about polygons. It's a very short chapter. Really, we're just going to cover two sections, and most of the material is in Section 1. First thing we need to talk about is polygons. The first thing here is, what is a polygon? Polygons are two-dimensional, so they lie flat on your piece of paper. They're made up of straight lines, so in other words, something like that would not be a polygon. Also, they're a closed figure, so something like that is not a polygon. What else? A regular polygon is a polygon that has all of the sides congruent to each other. So a square would be an example of a regular polygon. An equilateral triangle would be an example of a regular polygon. This would be a convex polygon, whereas this would be a concave polygon. Okay, there are some names that you do need to know for polygons. Obviously, you know what a three-sided polygon is. A four-sided polygon is a quadrilateral. Five-sided is going to be a pentagon. Six-sided is a hexagon. Seven is a heptagon, H-E-P-T. It's also possible to use this, septagon, S-E-P-T. I think our book uses hept. 8's going to be an octagon. 9 is a nonagon. 10 is a decagon. And then the ones you need to know beyond that are dodecagon, which is 12-sided. And 15 is pentadecagon. Anything else like a 27-sided figure would just be a 27gon. Clever enough, right? Oh, by the way, word problem up here. I actually think that is just, those are just misspelled words. Okay. Let's get to some of the formulas here. For interior angles, we know that a triangle, of course, has 180 degrees. A four-sided figure, a quadrilateral, has 360 degrees. With a pentagon, from one vertex, I can draw two diagonals, splitting it into three triangles. Each triangle, of course, has 180 degrees. So if I take all these angles of all these triangles and add them up, I'm going to get 180 times 3. So a pentagon has 540 degrees. Likewise, for a hexagon, from one vertex I can draw three diagonals, and it splits it up into four triangles. So it's just going to be 180 degrees times 4. So it's going to be 720 degrees. So if you look at this, for each figure, I can, so every time the number of sides increases, the number of diagonals I can draw increases by 1. So you can see here that a pentagon has 2 diagonals I can draw. A hexagon has 3, and it splits it into, more importantly, 3 triangles, 4 triangles, and then just, for heptagon would be 5 triangles, so on and so forth. So if I'm looking for the sum of all the interior angles, it's going to be, given n sides, it's going to be n minus 2, right? Because for a pentagon it was 3, for a hexagon it was 4, so it's going to be n minus 2, the number of triangles, times 180 degrees. And that gives you the sum of all the interior angles of a polygon. For the exterior angles, the sum of all the exterior angles, well, let's think about this. So if one of my angles on the interior is x, the exterior angle is going to be 180 minus x. So the sum, the sum of all the exterior angles, 180 minus x, times the number of vertices. The number of vertices is the same as up here, the number of sides. So we'll call that n. And we know that's equal to, if I distribute this, 180 n minus nx. Now, if I take the sum of all the interior angles, this is x here. Let's assume this is a regular figure here. So it's going to be n times x is the sum of the interior angles. So it's going to be n minus 2 times 180. That's the formula that we just did up here. And if I go ahead and distribute on the right-hand side here, it's going to be 180 n minus 360 equals nx. And then if I go ahead and move, I'm going to add 360 to both sides, and I'm going to subtract nx from both sides. So 360 ends up over here, and I get 180n minus nx. And if you notice, these two are exactly the same. These representing your total number of degrees for the exterior angles. And if you also notice, it's equal to 360 degrees, so it's just 360. The sum of the exterior angles of any polygon is actually always going to be equal to 360 degrees, no matter how many sides of the figure that I have. The last piece of information is the number of diagonals that can be drawn in a polygon. And it's given by this formula that we're going to talk about. So let's go back up to one of these diagrams up here. And let's kind of talk about this. So I'm going to erase some of this stuff over here. And so the number of diagonals that I can draw, like for a pentagon, it's going to be 2, right? I can draw one from one vertex here and one vertex here. Well, 2 from each vertices. So here's from one vertex, I can draw two. I obviously cannot draw a vertex, I'm sorry, a diagonal to itself, and I can't draw a vertex this way, a diagonal this way, nor a diagonal going this way. So there's 3 points always that I cannot draw a diagonal to. So that's going to be the diagonals. The total number of diagonals is going to be n minus 3, because I can't, again, draw a diagonal to itself from a vertex, nor to the two vertices that are next to it, next to the vertex. And there are n number of vertices that I can draw diagonals from. So here's one diagonal, one vertex. Here's a second vertex. I can draw a diagonal this way and another one this way. And then from here, notice I can draw one this way and this one, but this one here we already drew going in the first direction. So we can't count them twice, and you can hopefully see that there's always going to be ending up, one going one way and then another one coming back the other way. So we're going to end up with needing to divide by 2 so that we don't count the number of diagonals twice. And so that's the formula for the number of diagonals. Sorry, I didn't describe that very well, but that is the formula. Just going to pick a couple of problems here randomly to go over, and then I'm going to give you a homework assignment to try. Name of a polygon with 35 diagonals. So I can use this formula here. 35 equals n times n minus 3 over 2. Multiply both sides by 2, so I get 70 equals n times n minus 3, or 70 equals, distribute the n squared minus 3n. 0 equals n squared minus 3n minus 70. Do a little factoring here, n minus, what is that, 10, n plus 3, no, n plus 7, sorry. And then, so n equals 10 or negative 7. Can't have negative 7 sides. That makes this a 10-sided polygon or a decagon. That was problem number 1. Number 2 is just plug and chug. Number 3, some of the interior angles. Number 3 is just going to be, 1440 using the formula on the front side. N minus 2 times 180. Divide both sides by 180 and then add 2. You end up with 10 sides again. The answer is not always 10. And then let's just do one more. Number 6 down here. If 2 consecutive angles of a hexagon are right angles, so you have 2 right angles in the hexagon, the remaining 4 angles are congruent, find the measure of the remaining 4 angles. So I got to find the sum of the interior angles of a hexagon, which we found on the front side to be 720, I believe. And then I'm going to take that, 720, subtract 180 degrees from that to get 540, because there's 2 right angles there. And then I'm going to take 540, since they're all the same, and just divide it by 4. So it's 135 degrees. And that's it. Number 7 is actually a problem from the next section, so we'll talk about that on the next day. That's it. That's 10.1. And 10.2, quite frankly, is not any different. It's just a few extra harder problems. All right. Hope everyone's doing well. Take care.